You can all defrag a bit if you want. Raise your hand if you know what defragging means. 1, 2, 3. You're all old. You aged yourself. For the rest of you, back in the day when we had disks of spinning Rust, files were not stored in sequence, and wherever a file was stored, they had to move physical objects to read the drives. So it was efficient if all of a file was stored in a sequence. As you deleted and you erased and added new files, the spacing would get fragmented. And you could defragment the drive by reading everything and putting everything in order. It was glorious. Anyone have fun like watching the defrag screen, like moving things about? It's like, oh, it felt so good. So hello, friends. Last person have gotten a seat. Welcome to second last session of the day. I'm glad it was so late on a Friday, so at least some people knew where room 2 was. I had a hard time finding it the first time. Just because I'm curious, who here is currently working with distributed services or microservices, and whatever definition makes sense to you, use that. Quite a few. Who wish they were working with microservices? Who wish they weren't working with microservices? Okay, they win. Who's working with the monolith? Who's working with a distributed monolith? Yeah, isn't that fun? Okay, we're going to get back to all of these terms. Microservices has been a thing for years, and now monoliths are coming back into shape again, which kind of makes me feel bad because I've been doing this talk for a while before it was hip to talk about glorious monoliths, but now I feel like I'm just one of the crowd. But the pendulum is swinging back. So, I'm Glenn. I work at a small law tech legal startup trying to become a scale-up. It's called Justify. You get personal legal affairs in order and go online to do it. But to do this, we built an application, and we decided not only to not go for microservices and a distributed application. We had a conscious decision. It was tempting, though, because you want to do it. Like, it's called resume-driven development, because I could use all kinds of fun tech. But we decided to build ourselves a glorious monolith. Now, what is a monolith in practice? It's not hard to apply these terms. A monolith the definition is a large single upright block of stone, especially when shaped into or serving as a pillar or a monument. Anyone ever worked with a monument of a software? Or a large impersonal political, corporate, or social structure regarded as indivisible and slow to change. Who worked on that app? It's not hard to apply these terms to software we have been part of. And a monument, sometimes is a monument to remember all of those consultants that were on the project for 6 months before transitioning out. Large, impractical, slow to change, indivisible. Not positive terms, really. Microservices, they're an architectural style, structures, and application. And people talk about features like highly maintainable and testable, and loosely coupled, independently deployable, like that's an awesome thing. Organized around business capabilities, great. Owned by a small team, sounds awesome. All these things that sound very positive. And this is sort of the image we were given, where monoliths are bad and microservices are good. Except the zeitgeist is changing a little bit. But when people talk about it like this, they're serving a false picture. They're saying that every monolith turns into that, which is just this massive organic piece, blob, more than a monolith even. While the microservices are like neatly ordered and everything is nice. Well, starting out with a distributed system seems to be a good idea for many. But in reality, you're starting out playing that game on hard mode. It's like picking up, anyone played Elder Scrolls? Like, I never picked it up. I'm gonna play this game, I'm gonna put on hard mode. Like 20 minutes later, after dying 400 times, like, no, I'm gonna go back to something easier. It's cool if you make it and you get huge bragging rights, but it's going to take you unnecessarily longer and significantly more skill to actually do it. And I'm here to tell you that a well-crafted monolith is never going to give you up. There are some fallacies to distributed computing. Who has heard those fallacies before? Yeah, a few. The network is reliable, always reliable. Anyone have stuff in Azure Blob Storage these days or today in West Europe? Anyone get a call from someone back home today? Because today, blob storage in West Europe in Azure was gone. Like, nope, gone, away. So unless you built in redundancy in your configurations, like, no, I don't have blob storage today. We decided not to have that today. Latency is 0, always, from one side of the globe to the other. It does take no time, no problem. Bandwidth, infinite. We can send as much data as we want. Anyone in AWS clouds? Anyone been hit by inter-zone transfer charges in AWS? That's so fun that people have built entire consultant agencies that basically assist to find out where you're shipping data wrong, and it's costing you literally tens of thousands of dollars a month. Network is always secure. Nothing that travels across the internet can ever be broken into. Topology doesn't change, nothing happens, nothing goes anywhere, and there's only one administrator. There's just one person you can go to fix everything. He knows everything. It doesn't really happen that way. It's like, yeah, you're gonna have to talk to Sheila, no, you're gonna have to talk to Carl, maybe talk to, and back and forth. And transport cost is 0. Network is always homogeneous. There's no differences, everything is the same. Great. So these are unique or amplified when you're building a distributed system. These are things that increase your difficulty level when going in. These are the things that if you don't think about these when building a distributed system, will bite you in the butt. All of these things have to be handled when you're going down to the microservice path. Anyone know how old these rules are? They're like 30 plus years old. Around 30 years, plus minus a couple of years. So this is nothing new. People have known about this. We've just chosen to ignore them for the past 10 years or so. Now the monolith, also called the big ball of mud, which is a technical term, supposedly invariably devolves into this big ball of mud. The spaghetti code, the massive code files, disorganized code. Every change risks breaking 1,000 things. However, most of these problems can be overcome. I mean, there's limitations to it. Is it, really? It's too large to fully understand. You can't fully understand a monolith. You can't go into it, fully understand it. Can someone really fully understand your microservice topology and architecture as well? It's not that different. Slows down startup time. Entire application must be deployed for every upgrade. Impact of a change is poorly understood, and there's barriers to adopting new technology. All of these things are true. They're not wrong, but they can be overcome by using various techniques. So building a distributed system is playing the game on hard mode. Building a monolith without thought and discipline is also playing the game on hard mode. Complexity always increases. As something grows, complexity increases. This is practically a law of nature, entropy and all that. The problem with complexity is we introduce bits and pieces in our code, we create more and more connections between pieces. And these pieces increase complexity, not linearly, but increases exponentially. So you get to a point where every single change introduces a lot of complexity. What we need to do is, over time, introduce various complexity dampening measures to keep the complexity at a low and manageable level. The main reason for the problems in monolith is that you get different parts and they're not very organized. They're not clearly defined, and after a while you get this unmanageable amount of coupling. Coupling is a thing we want to keep low in our monolith. Coupling is how many connections, how many hard dependencies does your one thing have to other things. Instead of this mess here, we want something that is cleaner and more easily reasoned about. We want contained boxes, more defined, smaller boxes, and want to limit their connections to other boxes. This helps with a lot of problems, provided that we are reasonably smart when creating these boxes. We should be able to build boxes that are small enough to fully understand, small enough to not have a lot of complexity, and small enough to understand the impact of a change. We do this by creating borders around our boxes and thinking hard about how we cross those borders. Coupling is one measurement we have in our application. Another one is cohesion. Cohesion is a measurement of that things that belong together are together. So we want a low coupling and we want a high degree of cohesion. These things are the same or talk about the same thing. They belong together. Let's keep them together. Let's not spread them all over like butter spread on a sandwich. Now, zooming into one of these boxes, your box should have a clear boundary. It should be absolutely clear on what it communicates out to other boxes, what is internal stuff. It should be absolutely clear on how you define the public surface of your box. And inside the box, we'll define the details of our box. Let's call it the domain. The inner domain layer, and we have an outer application layer. These are terms that people recognize when people start talking about domain-driven design, and to be fair, domain-driven design lends itself well to building glorious monoliths. This domain layer is internal to our box. Nothing from that domain layer should leak out and be coupled to other boxes. The domain layer contains all of your business logic. This is where you put your entities, your aggregate roots, your value objects, your domain services, all of the things that reason about the things that belong in this box. All your rules, all your business knowledge is in that domain. By slicing these boxes right, you can go into one of these boxes and find a clearly defined subset of your app, and you can work with that. But someone's thinking, that sounds like a microservice. It is. Any change in the domain logic, in the domain there, is for business reasons. The application layer here decides how other boxes communicate with our domain. For this, we use our domain services, and we create application services, and we create data transfer objects. For instance, we can have, in our domain, we have a thing. Maybe we'll make a thing service in our domain, in our application layer. And our thing service will communicate out through a thing DTO, a data transfer object. So if another box wants to access our thing, it will call the thing service from the application layer. It says, hey, could I get a thing with ID number so-and-so, for instance? Sure. And the thing server will go into the domain, find the thing, pick it up, translate it to a data transfer object, and ship that in its simplest fashion. It's basically what it does. A thing service can have multiple methods depending on what actions you want to allow outsiders to have into your box. By doing this, you're making your domain, your thing domain, and all the other boxes loosely coupled. They have an abstraction layer between them. And abstractions solve every single problem in computer science except the problem of too many abstractions. But this is just the right amount. Controlling the surface that is available to other boxes is a key instrument in managing the complexity of your app. If you just allow anyone to do anything, then you're not controlling your complexity. Okay, we'll get to more details as we go along. So, using principles from domain-driven design, you create these boxes around subdomains or bounded contexts. Helps with keeping these things understandable. A box should be self-contained with all its logic and all its data. You can reason about the domain and such a box in isolation. And you don't need to understand all the other parts of the application. So you can bring in someone new. You can show them, hey, here's this domain. Here's how it works. We need you to make some changes to the business logic here. And they can go in and do that without affecting the rest of the application because we have this isolation layer between it. And even if the thing changes, the thing DTO doesn't. So we can change maybe some parts of the thing service, which we own and control, and everyone else is none the wiser. Now, boxes is a really poor name. In our application, we call them features. It is a pretty arbitrary name. Pick one that makes sense to you, context, domains, whatever. It's not really important, but I'll be calling it features from here on out. So these features and the communication boundary of a feature should be treated like a public API. You should be wary of changing the public API, but that is one of the advantages you get in a monolith. Whenever you change the surface area, you have instant access to all the errors in the rest of the application. If you change the name of a method or change the name of a property or something, your IDE refactors that across all your boxes, all the consumers, immediately. Worst case scenario with a microservice, everything is published as a client, you have to upload it to a NuGet feed, and you have to make sure that all the other clients download the same NuGet field, and then you have a whole lot of trouble with versioning with clients. Oh yeah, that service is using an old version of our client, so we need to upgrade that because we did some changes here, and we can't make these changes because there's a whole mess going on there. So refactoring is working like a charm in your IDE, huge advantage when building out your application, especially when you're starting out, where things are much more in flux than they are later. You should be conscious of the changes, what a change in your public API can affect, but in a monolith, you can get a very clear picture of what parts have a dependency on your part. The application layer should also handle external dependencies. Makes your domain easier to test because they're not dependent on any external service. Makes the code easier to test, but also reduces the risk from changing stuff. In domain-driven design, this is what's called an anti-corruption layer. So you have a little thing that stands between you and some external service. That external service could be another feature, or it could be a third-party service. It doesn't really matter. It's a piece of code that prevents concerns from external features to infiltrate and drive internal change in your domain, in your current feature. So we're starting out with this. One might be tempted to have a thing service and say that everyone wants something from the thing domain should use the thing service. And that might be fine for a while when things are small. But unless your application is trivial, the thing service will grow and grow and grow and grow. It won't stay small for very long, indeed. Also, having a single thing DTO, probably not a good thing either, pun not intended. Different situations might need different needs, and you end up with multiple things, something DTO, thing list DTO, thing short DTO, thing view in a edit screen DTO, thing delete DTO, thing this, thing that, and so on and so forth. These service classes have a tendency to grow with every possible use case and have DTOs that are either reused or have a bunch of them similar, that's next to each other. Anyone been in that situation? Yeah. So what we do is that we make request command handlers, along with specialized requests, specialized commands, or specialized responses. We basically make one for each use case in our feature. We group these in a single, I'll zoom in so you don't have to read all of it. We group these handlers in a single file under a single, not do group handlers in a single file. We group the request and response objects and the handler in one file. I like using a class with nested classes. It makes me use the class name when referring to handlers, less likely to have name collisions. So it's mostly a stylistic choice, but it does remove the need for some discipline. So here we have our query object, public record query. I request vault DTO. It returns a DTO from the vault. This is a handler in our vault feature. It has a vault user ID. It's in the nested class, get my vault. So this is a feature, this is a use case for getting my vault. Every user has a vault in our application where important documents are stored. So this is get a reference to my vault. How do I get a reference? I send in a query object. The query object has a vault user ID. It's the ID of whoever wants to get this. In this case, we have a DTO object that acts as our response object, but it could also be a separate response object that is here. So sometimes we'll reuse some objects across handlers, but other times we'll have separate ones. We're using Mediator for this as a pipeline, as the Mediator software. And the Mediator software acts on the domain's behalf. So our front end or API level or whatever, they don't have a dependency on our domain or on features at all, except for the different query classes. It has a dependency on the mediator, which takes in a query and then figures out who serves that query best. Mediator also has the concept of post and pre behaviors. So here we have, I require register vault user. That is a behavior that we attach to this query, which gets the current user ID from the login token and populates the vault user ID field automatically. So we'll say, well, I require register vault user. That's an interface. It makes us have the vault user ID, and it's automatically populated. Then we get a nice pipeline for that particular use case. And then we have the handler for that. This is the code for getting a vault user. Vault service, get and create vault for vault user, map that to a vault DTO, and a vault contains a bunch of boxes, and for each box, get the vault. Is there a partner? Because sometimes you have partners with your boxes. And then it's, it updates those as well. Yeah, because it can get or create, so it does it save changes. This is the actual handler. It's relatively easy to reason about, especially if you have some understanding of the domain behind this. This is what it does. This is also an element of what's called a vertical slice architecture, where every use case is one slice of your architecture, and every use case can use a different architecture. Right here, we're using entity framework. We don't have to. Maybe we have some hot paths that are called off, and maybe we won't use entity framework. Maybe we'll use pure ADO.NET. Maybe for some pipelines, we're using a store procedure and calling that instead. It doesn't matter. Maybe for some pipelines, we won't call the relational database at all. We're going to call a document database that has a projected view in it. It doesn't matter anymore, because architecture decisions are no longer a thing that you have to decide for your entire application, but you decide for that particular use case. Of course, it's always nice with some discipline, so we don't evolve into complete chaos, but we have the ability to do that if we want to. So this is the entire code file with the response, some dependencies, and the actual handler. We have lots of these. We make multiple ones. It is easy to fit the code in one handler into your head, and a feature needs information from another feature. We still like to use service over a mediator handler, because calling handlers from another handler is not really supported in mediator, and most of the features are to endpoints. But it also, if we have a certain naming convention, it gets pretty easy for us to go into a folder and say, okay, what are the things we can do with this thing? What can I do in a vault? I can archive entries, I can create entries, I can delete them, download them, get different things, move things, share things, unshare, and upload. Sweet. We can even pull our API endpoints into our feature folder. This is using the endpoint feature in .NET or ASP.NET, where we'll have add task endpoints. This is for adding tasks, mapping certain endpoints, mediator send, get list request. That's how you call a mediator handler. There are other libraries that do the same thing. Wolverine is a pretty good one that does pipeline handling. It does it in a slightly different way, an interesting way, but it's a really good thing. And then when you have all these things here, all your API endpoints, well, you can just add those. That's your startup class. Like, hey, add task endpoints. Or maybe you can go even further. You can have a startup class or add tasks that defines all the dependency injection, all the services you need, all the middleware that system needs, all the endpoints, and the box is very self-contained. Data is always fun. Another characteristic of microservices is they are autonomous, including with their own data. So how do we do this with our features? Should every feature have its own database? Sure. Why not? Well, because multiple databases are expensive. Sure, that's fair. We don't have to have multiple databases, but we do want to separate data access. Every feature should own and control its own data. In most databases, we use something called a schema as a namespacing functionality. We use entity framework in our application for the very most part, and each feature gets its own DB context, its own database definition, connection definition, its own unit of work even. So we have a vault, it gets a vault context. We have a chat feature, it gets a chat context. Some of you are thinking about data duplication. Do we duplicate data or do we read across? The number one rule is never integrate on the database level. You integrate on the application level. So yes, we have multiple user objects. Vault has a concept of a user, And chat has a concept of a user. These are not the same. They represent the same physical thing, but they are different representations. The things that happen with a Vault user are not the same as things that happen with a chat user. And not every Vault user is a chat user. Vault users for us are our customers, but they're also external people that have had a document shared with them. They also exist in our Vault user table. A chat user is only registered customers that have started a conversation with us in the chat interface. So now we have data duplication. There are mechanisms to get around that. I'll touch on that a little later. But these tables are not the same, and they will coexist in the same database, even though they're all both named user, because they have separate schemas, which works the same as namespacing in your programming language. We can even assign permissions, saying that some parts of application, or one app, is only allowed to access that schema, not that schema. We use a common DB context, a base DB context for this. Thank you back there. We have an object-oriented language, so we just inherit from a base DB context. It has an abstract property string schema that has to be overridden in a consuming class or a subclass. Like Vault context, it has to override schema. I'll say this schema is called Vault. And then on the on-model creating, in the base class, we say that this has a default schema. So this, using abstract properties, is a way to enforce discipline, to enforce our rules, removing the need for the developer to have that discipline on his own. We also like to use a lot of events. Now, events are not just for distributed computing. You can use events within a monolith. We like to call, instead of just calling other features handlers, we like to communicate through events because that makes our feature even more loosely coupled. We use in-process events, and Mediator is pretty good with this. We use a technique from Ardala's clean architecture, where we have our base entity class, which has a listing of domain events, where we add domain events and remove domain events. And then we have in our DB context class, we override the save changes function, and then we go through these events. And then we publish them with Mediator. That works very well for in-process events and what we like to separate in domain events and integration events. We like to, because some events have consequences internally in the domain, because this thing changed here, then this other thing changes here, and that's fine. These just happen within the same transaction. Then we have events. Some domain events should be translated to external events. This is how we do it. You might want to do it differently, but we found that having rich domain events using rich domain objects is helpful in the domain for handling complexity within a domain. And then we like to have integration events or external events that go outside the feature that use more DTO-like data transfer objects. They don't use internal types, they use external types. So we have little classes, handlers that pick up internal domain events and publishes integration events as those. And here's one of the things you need to be wary of. When crossing DB contexts, you don't, out of the box, have transactional integrity. So what we do is that we use the outbox pattern. The outbox pattern is you take your event, instead of publishing it to something, a service or whatever, we store it in the database. And then we enqueue a job that will pick it up later and actually send it. So we send a lot of events through what's Azure Event Grid, but it could be anything. It could be RabbitMQ, it could be Service Bus, it could even be in-process as well if you want an in-process event handler. We have some things that are separated on other machines or other services, so we use Event Grid to communicate with these. The events storage is also defined on the base DB context class. So every DB context gets its own events archive or event queue. So they are stored in the same transaction. Let's make sure that whenever we have events happening, the changes to my domain objects and all the events, external events that are based on those changes are stored in my database in the same transaction. So that means if something happens, either I get all of the changes and the events, or I get none of the changes and none of the events, and probably an error somewhere. So I don't end up in a half state where the changes happened and it was never evented. You can also, with Entity Framework, set up using shared transactions, where all your DB contexts are involved in the same transaction within a request. Your mileage may vary. Mine was, we were not thrilled with the option. It was too much configuration, and we weren't quite sure how it would work in our system. We thought this was a better option. Now, we have our clearly defined features, we have our domain objects, we have application level handlers, we have services, have their own corner of each database. External communications limited to sending off request commands. We register some services for notifications. We have all the groundwork in place. But in a monolith, what is stopping our developers from just referring to the internals in one feature from another feature? After all, if it's in the same application, there are nothing is further away than a using statement. So there's basically three options to this. One, you trust your developers and their discipline, which, if you say that to a manager, they're like, really? We trust people now? When did we start doing that? But I find that most developers are adults, quite capable of managing themselves and following a set of agreed upon rules. So depending on your environment, that might work really well. We have people tend to do the right things. We pair program. We review each other's code. We say, hey, oh, I see you did this thing here. That doesn't work. Some people like to create a lot of projects for your features, and they use features in your language or in the system to hide stuff. For instance, you can make classes internal for a feature. That way they're not available outside that assembly. You eliminate the possibility for other classes to reference other classes, because sometimes you can't create circular references. So this thing here cannot reference this thing here because this thing here ought to reference that thing here. And you create a graph of where references can go. But it's a very simple graph. You can go from here to here, but not from here to here. And you make either you make pretty big islands, or you make lots of small ones. I'm not a fan of that methodology. The multiple projects, the Whether we need an application project, a domain project, an infrastructure project, we need a web project. And then some people go even further. We need a feature infrastructure project, feature domain project, feature thing project, and whatever and whatever. I'm not a huge fan of that because it forces you to spread your feature out across your application instead of keeping it here. There's where it is. Everything is here. There's infrastructure, there's application, there's domain. Everything is in one place. Oh, but you reference infrastructure assemblies in the same project as you have your domain code? Yes, I do. Why not? Well, what if you access the database of your domain objects? Well, I don't. That's the discipline part. But there's a third option as well. You can use enforceable rules. There are frameworks that let you set rules on what part of the application can talk to what other parts of the application using namespaces. One such is NSDEPCOP, and you can make rules such as these, saying that everyone is allowed to talk to system, whatever, and everything justified dot star is allowed to talk to justified common star. Justify whatever dot application whatever is allowed to talk to justify star domain. Anything that ends in a namespace called .web is disallowed from talking to anything that ends in justify .whatever .domain. And if you're in web somewhere, you're allowed to talk to application namespaces. For instance, this is just a simple thing. You can make these as easy or as complex as you want, but these will generate build errors on your system, saying, hey, you're talking to something you're not allowed to talk to. And you can make multiple files, and so you can have these in your features as well. So in your feature, you can say, what namespaces are allowed to talk to my feature? What namespaces are not allowed to talk to what parts of my feature? And you can make a hierarchy of this, which makes, especially if you have larger projects, makes it easier to control who is doing what. And it makes it easier to fall into the pit of success. It makes it easier for someone new coming into the project and not doing mistakes because it was easy. It's like if you have tools, like if you have a proper IDE, using something from the wrong place is like control dot. And then your IDE just imports everything it needs. And you're like, yeah, that was easy, sure, nice. But then this stuff will come up and say, hey, sorry, you can't access that from here, so you need to fix that. Oh, great. So why do we do this? We are making things more complex than just file.new. Yes, we are. But the complexity we're introducing is actually pretty small. I talked to most of the complexity around here in about 40 minutes. The complexity is fixed compared to the complexity we get as an application grows. We have a lot of base classes. We laid foundation with pipeline handler, mediator handlers. We have a little foundation with who's allowed to talk to who. So we make a bunch of foundation things, a basic foundation of your house, and we just reuse that. What we're getting back is an application that's pretty modular in its built-up, with each module or each feature having a clear responsibility, being relatively small in size, being easy to reason about because of those things, and having fewer reasons for change. These are good things. These will help you going forward. Now, there are good things about microservices as well. I'm not going to trash it. Anyone heard of Conway's Law? A couple. Conway's law says more or less, and I'm paraphrasing because I'm not that good at memorizing, but any organization creating a relatively complex system will design a system with an architecture that's the same as its organization. So if you have an organization with a bunch of different teams and a bunch of different hierarchies, and your organization is making a complex system, if you look at the system and your organization chart, it will look the same. And if you have an organization with a bunch of different teams, as an organization scales, monoliths really don't scale well with them. Splitting out parts of your monolith to be autonomously managed by autonomous teams, that might be a good way to scale. Saying, okay, you folks over there, because if you keep clinging to the monolith and fighting the organization, you've moved all of the distributed fallacies from your software to your organization. So instead of all the stuff between services is now between people. Because all of these people that are not related, not connected, now have hard couplings through our monolith. And that's not a good thing. Part of the application might have different technical demands. We had one issue where we were running a lot of stuff on the Azure App Services, and we're generating PDFs, and we have designers who want a particular font for their PDFs. It turns out custom fonts and PDF generation on Azure App Services is not a good thing. They've later fixed it, but back then we had to split that part out and run its own kind of job in order to get custom fonts going properly. Because Azure App Services is a pretty sandboxed environment, and custom fonts didn't do well there. Scaling one part of the application individually. A monolith is deployed as a unit, and if you want to scale a part of the monolith, you have to scale everything. I talked to one guy. They had a login that you could log on to their app, and they've been taught well, so they encrypted and salted their passwords with a really hard encryption method that took a long time, because that makes it hard to make the brute force things. The problem was that this was a service that was used for a particular industry in the UK. So every morning, hundreds of thousands of people would log on at the same time. And their server would just go, and the thing that took the most time was the password encryption part. So they took that part out and put it somewhere else and scaled that enormously, which was a lot cheaper than scaling the whole application. So you figured out, okay, I have a reason to build a microservice, or at least start making a distributed application. If you're not careful, you make a distributed monolith with all the disadvantages of both sides of that coin. Like, yes, I would like those disadvantages, and I'll take those as well. It's not really a good idea. But you've been paying attention, so your application is ready for this. So you can start carving this monolith. You can start taking things out into its own service. The thing about distributed application, if you're not careful, you drag along all the couplings that used to be inside a process are now going across the wire. But we have our thing service, right? And our thing service clearly defines, and our thing feature clearly defines how other people should talk to us. And the thing DTOs clearly defines how we should ship data to other services. And we subscribe to events from other domains through external events. So it becomes relatively easy to take our little thing feature and put it on another machine. And back on the monolith, we leave a iThings service interface, which can be implemented with HTTP or gRPC clients. And because you've taken care in making the seams in your application explicit, it's relatively easy to cut along those lines and say, this thing now belongs over here. And we did hook this up to subscribe to events, but it already has the same event consumers that it used to have over there. They're talking to the same event system. If you have an external event broker, if not, you have to introduce that as well, which is not a huge amount of work. It's non-trivial, but it's not massive. Anyone still talking to your Things service does that through a well-defined API, public API. Anyone talking to all your endpoints, if they're API endpoints, they come with you. You just add endpoints, add feature in the new app. So carving out parts of your monolith and putting them somewhere else, if you follow the general rules, this process is never going to make you cry. So, summarize. Starting a new application with microservices in the beginning or distributed application, that's playing this game on hard mode. Lots of work, very little return in whatever foreseeable future you have. I call Yagni. You ain't going to need it. Most people don't. Microservices was a thing because Netflix started with it, but sorry, you're not Netflix. There are advantages to it. There are places where it is definitely valuable. I had one person come up to me after I did this talk some other place, and he was wondering what he should do because he's starting a new project in 6 months, and he has a team of 40 developers. You should probably start with a distributed application. Because getting 40 developers to start working on a monolith is probably going to be playing that game on hard mode as well. But you should be very careful on, maybe we should make a few monoliths. Building a modular monolith will give you many of the advantages of microservices, but very few of the disadvantages. And you get some extra advantages instead, like IDE support, refactorings. Requires a little more thinking, but the additional complexity is more or less fixed. Use services or events for cross-feature communication, making clear seams you can cut along when carving it out. The point of this is not to build something ready to be distributed, like I can do microservices any day. That's not the point. The point is to make a maintainable monolith. The carving part is a bonus. So, summarize again, good monoliths, it's never going to make you cry, it's awesome. Any questions? I have prizes if you want to ask questions. Yes, sir.
For example, like I have a created or modified by user.
Yes.
And this is an employee, but if you use separate contexts, you lose the relational advantages of the database. So
yes, so he also works with multiple DB contexts. And if there are some properties that are changed, like modified by, and then you lose the relational properties. True and no, because you duplicate the relational properties. For instance, if you have modified by as a user ID, you will have a user in every context that uses a user. And they are duplicates of whatever, for instance, the user feature, which has the master data. So whenever a user is created, we have events that make sure that that particular user exists in the domains that need it, or the domains that need it, they subscribe to a user event, created event, and they create their own version of that user with the same ID across these domains. so that I have a modified by ID here, which is related to a user here. So that's what we do.
In that case, you have a lot of duplicate data then for
Yes,
this case.
I have a lot of duplicate data. Doesn't matter, storage is cheaper than dirt. The disadvantage is to keep data updated, so you have to do that work in addition. We solve that, depending on the data, we solve it in multiple ways. Often we go by events. So usually we don't need a lot, maybe we have just the ID and the name, so we subscribe to name change events. So whenever a user changes the name, that is updated over there, that an event is published. In this domain, I have a user, I subscribe to user created, I subscribe to username changed events, and I make sure to update that thing. And this is code that is so common that we have a lot of that code in our common libraries, so we just pull in that handler and just do that thing. In other cases, we just have jobs that just synchronize across domains every night, saying, hey, I want all the customers, just give me that list and I'm done, because we're okay with the eventual consistency. That we pay that price, we pay that toll for data sync to avoid the toll of having hard couplings between domains. It's a trade-off, like everything else in this business. But it's an excellent question. Thank you for asking it. And come collect your prize. Or catch, if you want. Oh, there you go. Other questions? Yes, over there. He saw the mic and was ready to go for it.
Yeah, it was close. So I understand that it's a bit like microservices, but without all the distributed thing and network connections. But with data, you do duplications, so you communicate via events. So a lot of like microservices would do. Do you find yourself needing patterns like choreography or orchestration to like connect different features between, like if there are some time dependencies or things need to happen before one, or something waits for multiple events before it happens?
So kind of like sagas and orchestrating between different features. We haven't had a lot of that issues. For us, the seams we've been making have been pretty good at, so the question was, do we have the need to orchestrate things to happen across domains a lot? We have managed to avoid that problem. If you have that problem, there are well-established patterns to fix this, and it's the same whether you have a modular monolith or you have a distributed application, except it's actually easier to do it in the distributed monolith. We have things where something happens here, it creates an event, and then something happens here. But for us, we haven't had the need to orchestrate these. If you do that, I'd recommend looking at stuff like mass transit or N-service bus to handle the inter-feature communication events, which has patterns for doing this stuff. And all of that, whenever you have events orchestrated across feature, that is a business process that needs to be modeled, and the way you do it is completely dependent on your business state. So for instance, can you cancel an order that is in process? How does that work? Those are business decisions. So we haven't had to, but there are established patterns to do orchestrations and sagas, so I would just lean on those. Did that answer your question?
Yep.
Yep. Come collect your prize. I don't know. Intercept. Pass it back. Yes, in the back there, blue shirt. You have 48 seconds.
I just raised my hand for the chocolate.
Oh, sure, I can respect that. Come collect it.
Right. No, my question is around managing releases and deployments when you have multiple teams working on the same code base.
Yep.
So
multiple teams working on the same code base. Multiple teams is one of the reasons to go to a microservice or distributed application shape. When you do it, it's sort of up to you. You do it when it starts to hurt too much. We have a mono repo. Everything is in one repo in GitHub front end, back end, everything is there. So it's relatively easy for us to do CI checks, make sure that nothing breaks. Whenever someone makes a change, everything still works. We're sometimes working in 2 to 3 different teams on different things, and so far it works well. If we get a lot more, then maybe if we start allocating, and because all of our devs are pretty much all over the place, so it works well. Eventually, we'll probably grow to a point where we start assigning more like, okay, you folks work over there with this thing, you folks work over here with this thing. Then maybe it makes sense to split things apart. But even then, I'd be hesitant because since we're working in features, it's perfectly fine for someone to fix something in that feature, work in that, and someone else to work on that feature and not step on each other's toes. And since we deploy often and automatically, so whenever someone does something, it's in production shortly after, so we don't really have to wait to coordinate different deployments and anything like that, because when we're done, we ship it and it gets deployed, and nothing goes in to our main branch without being production ready. So for us, it's not an issue, but if we grow, especially as your organization grows a lot, then this becomes a problem. If you have a hierarchy in your organization, then maybe you'd split. Yes, this was time. Come up and collect your chocolate. I'm not going to throw it down there. If anyone else is wondering, you look for the guy in the pink t-shirt. Thank you.